Hello and welcome back to the SOFiSTiK For You YouTube channel. It's quite a long time since I posted the last video, so I hope you really enjoyed this video today. Just recently I published a mini course about the SOFiSTiK Grasshopper workflow. In this course I actually explained how you can set up a simple truss system in Grasshopper and connect the geometry to SOFiSTiK to perform the analysis and the design. Today in this video I would like to pick the similar example, so this truss system, and do it actually in CADi, so the text editor in SOFiSTiK. So we will do a full text-based example today. You can see here on the screen, this is the example. It's a simple truss, and what we are going to do is we will create, based on this information we see in front of us, the principal structure, and we will also parameterize it. So you can change the number of segments, the height and the length of the truss, as well as the value of the loads we are going to apply on the top joints. So let's have a look into the different member names of this truss. So you can see the top chord member on the top, on the bottom we got the bottom chord, and we got vertical members and diagonals. So we will use those terms during the example. Then three variables will be set up at the very beginning, which are the total height of our truss, as well as the length, and of course the number of segments. And we will use the length and the number of segments to calculate actually the length of each single segment for our truss, to then build of course the geometry. So I would say let's get straight into the input. So what I have in front of me is now the SOFiSTiK Text Editor 2020, and I have already created a new example here. So on the left hand side you can already see the user manual, which is quite useful, especially when you start using the text input, but also for more advanced users. So on top of this user manual I will also open the module tree, because along the project we will set up a couple of program modules, and it's quite helpful to have this navigation in place as well. You can activate the module tree here on the left. Let's get started. The first program module we need is the program module Aqua to set up the design code, the materials and the cross-section. Therefore we enter prog Aqua. For the header we enter design code, materials, and of course the cross-section. Okay, good. So first of all, I will introduce a label to get a better navigation in my input, and therefore I go to Insert and click here on the label command. The label will be just the design code and materials. Okay, good. So now I go ahead and define now, first of all, the design code, and by using the command norm, I can look here in the user manual what's available. So first and foremost, I enter the item DC for the design code, and I will stick with the Euro code, and the designation of the specific design code is entered in the item NDC. So I will use the Euro code 3, which is 1993-2005. Okay. Then I will also create a steel material with the command STEE for steel. The number of the material is 1 and the type will be a steel type. And the classification is 355. You can change this later on, of course, as you wish. So I have actually used all capital letters, but the input here is actually not case sensitive, so you're fine using also small letters if you want to. Let's introduce a new label to create actually the cross sections. I actually love using these labels because it's quite useful to navigate through the script. So you can see it already here in the module tree. We can see now the design code, the materials label, and the cross-section material, and also the cursor jumps at a particular position. Now we have just a short script which doesn't make sense that much, but as soon as that gets longer, it's really helpful. So to create a cross-section, we will actually build 3 cross-sections. For the cross-sections, we will use standard cross-sections, and we can see them here on the screen, which is for the bottom and the top chord are the same cross-sections, RHS 150, 110 millimeter thick, and then we got an SHS 60 times 5 for the vertical members, and an SHS 110 for the diagonals. So we will create those cross-sections now by actually picking them from the available library. So therefore we use the command prof for profile, and the first number is of course cross-section number 1, and I enter as a type RHS for the top and the bottom chord, and for the value Z1, so the identifier of the shape, I enter now the information of my cross-section, which was 150. For Z2 I enter 100, and for Z3 10 millimeters. I also put a command here at the end which says top and bottom chord. So later on when I use the cross-section or I want to change something, I can easily spot where I actually need to go to. Okay, the next input will be the second profile, and this will be the profile for our vertical sections. So I will duplicate actually the input line by using the F8 function key. And first of all, I remove the command here and I write vertical members. And then I change the information from an RHS to an SHS. And for Z1, I use 60. And the thickness here is 5 millimeters of our profile members. Okay, let's go ahead, create the third section, which is the cross section for our diagonals. I hit the function key F8 again, change the cross section number now first and foremost. Then I will change here the command, which will be diagonals. Okay, and this will be an SHS 110. Okay, good. So basically the cross section is, all the cross sections are defined, and we can go ahead with the input. But before we do that, let's calculate actually what we have created so far and double check it in the report browser. So I go to the home menu and click on immediately. The immediately command allows you to perform everything. So, and we see actually we ran into a problem, and the problem was actually I simply made a typo in the design code. I didn't enter 1993, I actually entered 19,993, which is absolutely wrong. So I go over here in the input of the norm command, correct my mistake and calculate it again. Okay, we're good, green tick is fine, and let's open the report. In the report we can see already the defined material over here, and also our cross sections pop up as we have defined them. Great, so that works. Then let's look into the next part. What we need to do now is we create our structure, so the geometry. And therefore I use the SOFI Mesh C program module. So I start with proc SOFI MSHC, and I need now to initiate a new system. And this happens with the command syst. And the type of the syst is 3D, so I work in the 3D system, and the group divisor is set to 10,000. So these are basically default values. Then I need to tell the program that it should also mesh my elements, which I'm going to create in the next minutes. Therefore, I use the command control and the option mesh. And I set the parameter to 1 to mesh beam elements, as I'm going to create beam elements. Then also I want to tweak the mesh size, and therefore I use the control opt command, which is hmin for the length of the minimum length for my finite elements, and I enter 0.5. Again, you can tweak this information later on if you want to. If you don't define this hmin, it will pick simply 1 meter as the default. Okay, then I can go ahead and start with my input of the geometry. Before we do that, as we mentioned earlier, we are actually interested in creating something parametric. So we need to define our parameters first and foremost. So you remember at the beginning I showed you actually what different parameters we are going to define, and those are the ones we have: the height, the length, and the number of segments. So let's go ahead and define now those through parameters. And before I do that, I simply introduce a new label, and this label says system variables. System variables. Okay, here we go. And I go ahead and define a global variable, which is the slope parameter, and I use h for the height. Let's make a capital H. And the value shall be 1.0 meter. So I haven't discussed any units here in the system. I stick, because I have used the Eurocode as my design code, with the default units, which means the system parameter or the system unit is a meter and cross sections are in millimeters. So I can now, without any further information about the unit, simply enter 1.0. However, if someone else uses the script, it's also good to put a command, for instance, with an information that this needs to be entered in meter. Okay, let's define the next variable, which is here in our case the length, so the total length of our structure. And this shall be, for the beginning, let's do 7.0 meters again. So I will also put this command over here. Then the last variable we want to define is the segment, so the number of the segments. And for the beginning, I will start with 4 segments. And here in the command, I simply use something like this, so everyone knows it's without a unit. And you could also say something an integer, so that no one actually enters 4.1 or something like this. Good, so these are the variables we are going to define. And we can actually now jump into the definition of the geometry itself. And for the geometry, when we just scroll a little bit down and create a new label, and the label will be geometry. Okay, we actually will define structural points. And let me show you quickly the structural points I have in mind. So it's when you actually use the text interface or programming in general, it's quite important to have a clear structure of a system in your mind before you start. So what I will do is I will create a couple of nodes, and those nodes have the number 101 to 105, just as an example over here. This could be also 107, 8, 9, whatever, and up to 199, because from 201 onwards, the top chord actually starts counting. So basically the joint nodes of the top chord. So for me, it's clear later on when I see a point which starts with 100, I immediately know this is a point of the bottom chord. Similar for the 200 node series, I understand if I pick one of the 200 nodes, this is some information from my top chord. Before we can start, we need to calculate actually each single length of our segments. And we have now 3 parameters defined, which is the total length and the number of segments. So we can simply divide these 2 values to end up with our segment length. And to have the segment length available later on in our script, we create a variable. And this time I use a local variable, because the idea of having this global variable would be to simply pull out this whole block of global variables and place it at the very beginning of my script, for instance in the template program module, which kind of saves you time to scroll through the script to find actually where you have to enter particular information. However, the let variable is just necessary, or at least here what I prepare for this particular part of my script, so I can keep it local, so there's no need for me to save it in the database. And for the name, we use segment length, so seg length. And the segment length is actually simply division from my variable length divided by the variable of the segments. Okay, good. So now we have this out of the way. We can look into the generation of our 2 node series. Therefore, I start with the loop, and I use as an iterator I. And this loop shall go, because we need to create a series of the nodes, so the entire number of segments plus 1. So if we look here in the sketch again, so when we would use just the number of segments, we will create the node number 101, 102, 103, and 104. So we'll basically miss out on one run of the loop, and we are not going to define the node number 105, for instance. So that's why I need to enter here as the number or the end number of the runs plus 1 to the segments. And immediately after I created the loop input line, I also close the loop with end loop. This is quite useful, because if the script gets more complicated, you might easily lose track of closing the loop, and you might run into an error when you calculate it. Okay, so we have now the loop. This runs now 5 times to create our bottom chord nodes. And to create now these structural points or these bottom chord joints, we start with the command spt. And spt, as you can see here on the left-hand side, is the command for the structural point. And we start with the structural point number 101. And as we are in a loop, we need to increase it every time it runs through. So plus the iterator hashtag I, and we have completed the number. Now we need to enter the coordinate. And the coordinate in the longitudinal direction is the x direction. And what we need is simply the length of my segments. So I enter the segment length and I multiply this with my iterator again so that it increases every time the loop runs, and I end up with the new x coordinate. Cool. Then let's enter the y coordinate, which is 0, and the z coordinate is also 0. Don't forget the blank here. Okay, good. So we have completed actually the bottom chord. Now let's do the similar thing for the top chord, and I use again the function key F8, and I change, of course, a couple of inputs. So you remember our nodes are in a series of the 200, so I enter here 201. And for the x coordinate, we can keep that as it is. However, we should only change the value of the z coordinate, because this is now minus hashtag h. Okay, good. So basically this is the input for our nodes in the bottom chord and the top chord. And now we could actually look straight into the definition of our structural lines. But before we do that, let's calculate what we have in place here. So I also recommended that you perform several calculations to see if the script works properly or if you run into any problems. So I calculate this by hitting the immediately button over here. Aqua runs, SOFiSTiK runs as well. Let's look into the report, what happens. So we can see now the similar output as before. SOFiSTiK gives me the script, however, no information of my structural point. So I can actually tweak this by using the echo command and use as an option full, and also the value set to extreme to extend the output as much as possible. Let's calculate this again. Here we go, Aqua done, SOFiSTiK, and I click again in the report, and I can see now my structural nodes we have generated, which is actually great. So when we double check here, the node number 105 has the x coordinate 7.0. So you see it's accumulated the x coordinates quite nicely in our loop. Okay, that's done. Let's start with our bottom chord. And again, I'll use a loop. I just enter loop again, hashtag I, so I can keep the same iterator number. And this time the loop shall run to the segment, but with the total number, so we don't need to increase it by 1 as we did for the nodes. And don't forget to end loop. Okay. And what we now need is, instead of creating a structural point, we create a structural line. So I use the command sln for structural line, and the number needs to be entered. And when we head back to the sketch over here, we can see a couple of structural line numbers. So I created kind of a principle how I want to number my structural lines to keep track of them. And you can see quite a similarity as to the structural point. So my bottom chord is with the hundreds, then 200s is used for my top chord. And then I have also for my vertical ones 301. For half of the diagonals is 401 upwards, and also 501. So you see I've already created kind of a scheme in the numbering as well. Cool. So we are in the bottom chord now, and as we can see on the sketch, we are in the 100 series. So I enter for my structural line number 101, and again plus my hashtag I to increase the number every time the loop runs. Then important, we need to create a structural line between 2 points, and we now need to refer to the points we have created earlier. So I use the command mpa to refer to the start point, and the start point will be 101, so the first point of the bottom chord, plus hashtag I. In the first run, actually plus hashtag I 0. So you start at the node 101, which is great. And now for the endpoint NPA, we also use 1, 0, and 2. So it starts actually from this node number 2 plus I would be 0. In the next loop, it will increase by 1. So the second structural line 102 will start from the node 102 and end at the node 103. Okay, so and we're not done yet, so it's something quite important. Now it's time to assign a cross-section. And I do that by the command SNO, so section number, and for the bottom and the top chord we had the same cross-section number, which was 1. So let me just increase this. I will also add a command which says bottom chord. So later on, when I browse through the script, I find immediately what's going on here. So let's do that also for our top chord. So I simply copy the input, change this to top chord. The number of segments now needs to be changed because as you see here on the screen again, this sketch of the structural line numbers, we actually miss out on the first structural line we had in the bottom chord and also on the last one. So we need to reduce the number of loops by 2. So use segments minus 2. So we get, in our case, only 2 loop runs. And also we need to tweak something in the structural line generation itself. First and foremost, we change the structural line number. So instead of 101, I used 201 as the base number. And for the start point, we now are in the top chord. So we definitely need to change to the 200 series. And also we will start not from the first point, no, we will start from the second point. So the first structural line will be created between 202 and 203. So let's correct this over here as well. Okay, that's it actually. And we can actually run the script now. I will do that. So I go on immediately. I will now open System Visualization. And what we see is actually already our bottom chord and the top chord. Okay. Then let's proceed to the next information, which are the vertical members. And for the vertical members, let me bring up here this sketch again. We have the numbering 300, 1, 2, 3, and so on and so forth. And as you might already imagine, we use a loop again. So I copy the entire input of my top chord, change this to vertical members. Here we go. And I change this to 301 for my structural line. And now I look into my start and end numbers. We create the first vertical member between the node number 102 and 202. So I enter 102 and 202. And we can also increase this loop, this start and end point by 1. So we keep also the iterator hashtag I. We should actually change, of course, the cross-section number to the cross-section number 2. Let me scroll up again to show you. Here we have defined the vertical members. The vertical members had actually the profile number 2 and the diagonals profile number 3. Okay, let's go down. We might also want to assign a hinge, and we will do that straight away. So the hinge for the beginning of this vertical member, I just see a typo, members, I use the command fix a. And for the fixation, we at the beginning we use and sorry, not fixation, actually is a hinge, so I don't want to have any moments in my hinge. So I enter here and also for my end I enter fix e When we scroll down over here, we should find it somewhere. Should be, yeah, hinge condition. So we see it will simply unlock the torsional moment, the my and the mz of my structural line, which is actually what I want to achieve here for the vertical members. Okay, now as we have our vertical members and the top chord and the bottom chord in place, let's look into the diagonals. So I use a loop again, loop hashtag, and the iterator is still I. and I close the loop with end loop. Okay. Now we need to find a way how often the loop shall run. Let's go back to our sketch over here. And when we look into this graphic, we see for this particular truss, we got the total number of segments of 4. And on the left-hand side, we got 2 diagonals. On the right-hand side as well, 2 diagonals. So important for this example is that we have a symmetrical system. And this needs to be documented somewhere at the input first and foremost. So what I will do now is I go to the top where we have defined here our variables of the system, and at the input I need to add additional information so that the user actually understand what is allowed to enter. So we need to have at least 4 segments, so minimum 4 segments and even numbers. So we can only use 4, 6, 8, and so on. Okay, so we have this out of the way. Let's look here into the definition. So as we now distinguish between the left and the right half of our system, we need to divide basically the numbers of segments by 2. So enter hashtag SEG divided by 2. And this means that for our particular system, the loop will run twice. Okay, and I will also enter here the hint diagonals. Good, so let's start with the structure line. I can actually copy the one from here to save a bit of time. And I start with the number, and this is 401. And this is fine, plus the iterator. Then NPA, the start point is now the first start point of the bottom chord, which is 101. Plus the iterator, and the endpoint will be 202, that is fine, and the cross-section number is 3, and I will keep actually the fixation as well. Let's duplicate this input line and change the structure line number from 404 to 501, and I go ahead with the NPA, and now it's not totally tricky, but however we need to consider the fact that by having the loop in place, the iterator gets increased. So basically what we actually need is to decrease the number of our start point and end point. So we have to know actually the highest node number of our system. And this is simply this start node number 101 plus my segment number minus the iterator of hashtag I. And for the endpoint, we will have the same. Let me just bring this a line. And I start actually with 201 plus my number of segment. However, now we need to decrease already one segment number because we not start actually at the very end because there's one gap actually. So we miss out on the first and the last segment of our truss, and we also need to decrease here by the iterator hashtag I. The cross-section number can remain as number 3, and also fixation or these hinges at the start and the end point are fine as well. Let's calculate this and see what we get. Again, I clicked twice on the command. And here we go, we can already see the result. Let's go up and test this actually also for 6 segments. Calculate immediately. Yeah, looks good. It seems to work. And make a test with 5 segments. We should run into a problem, or actually not necessarily. Yeah, it simply creates 5 segments, but it will run into issues, of course, in the center segment, as we didn't cover this actually with any rules in our loop. So that's why it's very important to make it clear from the very beginning what is allowed to enter. If you want to get it also in the direction to be able to enter 5 segments, then of course you have to check this input within the loop with some if conditions or something similar. Okay, good. So I remain with 6 segments here. Now let's go down and look into the next thing we need to do, and this is actually the definition of the supports. So let me create a label quickly, insert a label and enter supports. Okay. And now we do the following. We have already structural points in place in our system. Now we will simply modify the first point and the last point and add some fixation information. So I start with SPT and with the node number, and I want to modify node number 101. I place simply a minus in front of this so the program knows, okay, a modification happens now for this node. And for the command fix, I use ppmx. pp actually means that we simply create a fixed support in the px, py, and pz direction. And the mx is simply a fork support to keep the system stable against rotation. Let's do this again also for the endpoint. And the endpoint is now actually 101 plus the number of segments, similar input as we did earlier for the diagonals. And we need to do that in brackets that actually the program can resolve this before it actually assigns this value to the item. And I also enter here the minus so the program understands, okay, this node number needs to be tweaked with the new information I enter. And this is fix, and I use py, pz, because I want to have a movement in the longitudinal direction, but I also want to introduce the mx support. Okay, and with that, let me just remove the empty space here. I calculate this again to double check what's there in the visualization. Here we go, we got everything in place, our fixed support. Let me just reduce the cross section. We see the fork as well, and also our hinges pop up quite nicely. And we see also here the support condition, which is able to move in the longitudinal direction. Okay, so we got now the structure in place. Now it's time actually to look into the definition of our loads. And for the loads, we use the program module SOFiLoad. So I start with the program module SOFiLoad. And for the program module SOFiLoad, first and foremost, we need to define an action. And the action is actually a container which allows you to assign loads to it. And these action containers can then be used in the design combinations. We actually don't cover this here in this example, but it's also good to define those containers for the future. Maybe you want to proceed with this example, bring it up to the design as well. So I use the type, and the type is a G for permanent actions. I duplicate this and replace this by Q. So G and Q is already available in the PIC design code, so I don't need to enter any combinations or safety factors manually. Now let's create a self-weight load case, which is done by the load case command and the number 1. So you can use any load case number, but it makes sense to start with the load case number 1 for the self-weight. And I use type, and as the type I use G, so it's saved in the permanent load action. And the factor or the dead load factor will be 1.0. Okay, this is actually the input for a self-weight load case. Now let's introduce also a couple of more load cases. So for each single node in the top chord, we will add single load case, and this is done by loop again, because the number of the load cases varies, of course, with the number of the segments. So let's start with loop, hashtag I again, and loop. And we will use the command load case, similar as before. The load case number is 11 plus hashtag the iterator. So I start with load case 11 and then increase by 1 automatically. By the loop, I use Q because I want to assign this load to my action Q. And the title is now node, for instance, and I want to increase this node number in my title by 1 every time the loop runs. So I enter here 1 plus the iterator, and that this information gets resolved in the command. I have to put it into parentheses and put the hashtag in front of it. Okay, let's focus on the point load. So I enter point for the point load. And the reference for this point load is a node number, and the node number I have already created. So I already know the numbers of my top chords, which is fine. And I use the note number of the series 200 basically, and start with the note number 202 plus my iterator #I. And the type is now not the action type now. This is now the type in which direction or the load points, and we have here the PG, which means it's in a gravity direction, so in our case vertical, which is absolutely fine, and the load value can be, for instance, 2 kilonewton. As we have a parametric script, why not parametrizing also the load value? Let's do that. Let's go up over here to our input and let's create a new global variable, which is, I don't know, let's do p load, and this shall be 2, and 2 is then kilonewton, right? And we simply use this variable, bring it down and replace the value 2 with the variable. So every time you change something over there, it will also update here in the bottom. And again, this is also kind of great if you define global parameters. You can reuse them in different program modules. And yeah, which also makes sense. Cool. So with that, let's calculate this script again, just to see if everything is set up properly. We don't run into an error. Here we go. We have already created an error. So let's see what happens here. So no condition for if or loop found. Let's see what I have done wrong. Let me see. Here we go. Actually, the number of the loop iteration wasn't defined, so I maybe was too quick, too excited about this topic. So we need now, of course, also find an end of our loop, and this is again referred to the segments -1. So if we look back to our sketch, let's go to the notes. We have exactly in this example 4 segments. So basically we need 3 point loads, right? It starts at the point 202 and it should count up to 3 times. So basically number of the segments -1. Okay, let's go ahead and calculate this straight away. And the calculation runs Aqua SOFiMesh C. So this is quite quick. Let's go ahead here in our visualization. We can't see anything. The reason is simple. We haven't performed any analysis of our load cases. And this is the next step we need to do. So we use the program module ASE. And this is the advanced solving engine of SOFiSTiK, and actually does all the heavy lifting for you in regards of analysis. And I will use the command load case, and the number of the load case is not a specific number. I have 4 load cases, or 5 actually in the moment. And I simply want to calculate all of them. And therefore I just enter for the load case number all. And let's calculate this straight away to see if we get some results. Excellent. And here we go in the visualization. The load cases are available, and I can also switch on the cross sections. So we got also the results, and yeah, we can see when we go through the different load case definitions, which looks kind of nice. Let's do a quick check actually in SOFiSTiK graphics, just to ensure we have really applied the loads at the right nodes. And I go to loads, input loads, all loads, and I will pick a load case number 1. So let me increase the font size. We got 2 kilonewton. Here's node number 2, 3, 4, and 5. So I guess we did a good job here. Okay, so let me just go back here to the visualization. Okay, with the calculation done, and yeah, kind of checked all the inputs in SOFiSTiK graphic. Let's do one more last thing before we conclude the session over here. And this is simply cutting out this input, bring it to the very top. So actually that the user don't need to browse through the script to actually find a particular position where to enter information and tweak actually the system. So what I do is I use the copy paste command. So Control C and also Alt C, which comments out the entire selected block. I go to the very top and I enter proc and template. Okay, so and now I simply paste all these inputs over here. And as you can see now, all the necessary information for the user is at the very top of my script. There's no need to scroll down to look into anything of it. And if you make it clear from the very beginning what is allowed to enter, there shouldn't be an issue, right? So, and let's give it a shot actually. Instead of having the length of 7 meters, let's go to 5 meters, and the height shall be, I don't know, 0.5, and segment 6 is fine. The load is 5, for instance. And let's calculate this immediately. Okay, good, and double check. Here the output, here we go. It's all there, and also our results are updated as we want to. Cool. With that, we're at the end of this video, and I really hope you enjoyed watching it, and more importantly, you really learned something about the text interface here in SOFiSTiK. If you just started off using the text interface, I can highly recommend to enroll into the Text Input in SOFiSTiK FEA Fundamental course. I will leave a link in the description below so you can start optimizing your scripts and of course increase your efficiency. I hope to see you in one of the next videos. Have a great day.